Okay, hello everyone, everybody. I hope you started a great day and had a wonderful time. Let's start today's session. Before I start talking about the new concept, I wanted to ask if anyone has any question regarding the previous concept or uh, generally regarding our course. Is there any question? Guys in the Zoom, do you have any question? Okay. Okay. So no question, huh? Okay, let's start today's session. So far, uh, let's review what we did. We learned about the switches. We learned about the topology of the inverter. We talk about the PWM, which is the way that we control the switching in order to like convert DC to AC current. And we went through the THD definition and talked about, okay, what is the quality of how we could quantify the quality of an output of an inverter, the output of an inverter. After that, we talked about the control system and we talked about the grid following inverter. We categorize the inverters to grid following and grid forming. Oh, before I forgot, before that, we categorized the voltage source and current source. We talked about that some inverter are voltage source, some are the current source. And then since we are going to focus on voltage source, we moved on. So our assignment using the voltage source, and then we talked about the interaction on the categories of the inverters regarding how they would interact with the grid that they are connected to, and we then categorize that as grid following or grid forming. We talk about the grid following inverter. We talked about their benefit. We talked about their parameters. We talked about their shortcomings. We said, okay, if we want to like have a grid following, we need to have a good control system in order to like follow the grid demands. We talked about the PID controller and talked how we could like control the active and reactive power control in our output of the inverter. And we said, okay, since the frequency is a critical parameters and we have to always be at the same frequency as the grid and we don't normally tolerate variation on that. We talked about the synchronization and we said, okay, if we want to like have a grid following, we have to synchronize with the grid in order to keep that frequency condition met. For that, we talked about the PLL and we talked how we could implement the PLL, how the PLLs work, phase marked blue PLL, in order to make sure that our inverters are synchronized with the grid that they are connected to. So this is how far we come through the course. Now, today, we are going to introduce or like talk about the other category of inverters on the perspective of how they would react when they connected to the grid. Okay, this category is named grid forming inverters. Okay, now come on, work with me. Okay. Okay. Why we need grid forming? If the grid following working for us, why we need grid forming? What is the motivation of actually like introducing this new kind of like techniques or technology or like control system if in the back end of that definition to have a grid forming when the grid following inverter is working for us and generally works for several years. Okay, so what is the motivation that we need to have a grid forming. One is we talked about that a little bit briefly on the last week, the first session of the grid following, and we said one of the differences between the inverter-based resources and the conventional generators, those rotary machines, are that the rotary machine has inertia. Okay, and if any transient happen, that inertia could handle that transient to a certain level. Okay, so that inertia, okay, which by the way, the definition of inertia means a resistance to change. Okay, the ability of a system to resistance against a change. So that's the definition of the inertia. Okay, so when a system has an inertia, therefore it can resist against the variation or any transient kind of like fluctuation. Okay. Now, the problem with the inverter is that we don't have any physical inertia as we had in a rotary machine. Okay, so if any transient happen and the grid itself cannot handle that transient, inverter definitely would not be able to like respond properly to that transient. Okay, so one thing is that the inertia in inverter-based resources doesn't exist. Okay, this is the one of the reasons. Another one is that, as you know, the control system of the inverters, the inverters works very fast compared to the traditional like rotary machine system. In rotary machine, the control system would respond to the change, but in order to give to that rotary machine to transition from the previous state to the new state, there is going to be a delay. Okay, we are going to need a time to transitioning from one state to another state when we have a mechanical system. On the other hand, in inverters, we don't have that delay. When you change the setting of the inverter's control system, the output instantly would change. So there is no, so that means any kind of variation at the output, at the terminal, okay, any errors that are going to get input to that PID controller or that PLL synchronization system, okay, instantly get an answer and it would affect the output. That means the stability of the inverter-based resources, the output voltage of the inverter-based resources is very fragile. Okay, it doesn't have inertia and it instantly answers to any change. So sometimes some changes you have to ignore, because it's temporary and it wouldn't affect anything, but inverter do not do that. Okay, so basically, okay. What is another motivation for that? Now, all that we said about the grid following is that the grid following relies on the terminals that is connected to the grid for itself to come up with the parameters and set the output. So basically, grid following relies on how strong the grid is on the stability part. If you have a weak grid, you can search about the definition of the weak grid. We are going to talk about that a little bit later on after the break. But if you have a weak grid, that means your point of connection, which is basically the reference for control system in grid following, is not reliable enough, is not trustable enough. Okay, so that means the whole output, the whole control system is not going to be trustable. This is a system. If the input is faulty, doesn't matter how good the system is, the output are going to be faulty. Okay, so this is kind of like the situation. So depending on a grid means in a weak grid scenario, when there is like a huge fault or a huge variation in our grid system, okay, would severely affect the performance of all the grid following inverters that are connected to that grid. Is that clear? Now, the fourth one is the black start capability. Now, before I explain that, anyone knows what is the black start? Anyone heard about the phrase black start in the system? No. When you have a power system, let me see if anyone in the chat room, guys in the room, in the Zoom meeting, any one of you have any idea of what is the definition of the black start is? No? Okay. Let's just start by defining what is the black start is. Okay. When you want to like activate the grid, black start meaning activating, injecting power when the grid is fully down. Okay. Another way to define that. You, in a regular condition, your grid is working. You wanted to connect to already existing dynamic. You have a power injection, generation, consumption in your grid system in a normal sense. Okay. Now you want to connect to that. Now, what would happen if all the grid system is shut down? Like it happened, I think, a decade ago in the United States too. Okay, so all the grid gets shut down. So nothing works. Now, if nothing works, there is no voltage, there is no frequency, there is no power demand and generation, nothing. So how how an inverter could start when there is zero information at its point of connection? That is starting from zero, we call it black start. So everything is off. Now we want it to start. Okay, time equal to zero. This is a black start. Now, black start capability doesn't exist in grid following because grid following needs information of the grid in order to set the output. Okay, if the grid is off, that means there is no frequency. So the frequency is zero. So PLL wanted to keep that frequency at zero. So the grid following inverter would not work. Are we good? So grid following inverters do not have the capability of a black start. When everything is off, they cannot get on and start supplying the energy. They have to have, it is like a mandatory requirement that they have to have a functioning grid in order for them to be able to like respond and generate power or inject reactive power or consume reactive power to the grid, or active power, injecting active power to the grid. Is that clear? Now, another way to think about that is sometimes, as you know, the protection system in the system would act and isolate a portion of a system to prevent the kind of like propagation of a faulty kind of like situation. Okay, now we call that isolation an island mode. Okay, now it's not connected to the grid, it's separate, it's like an island, separated from the rest of the grid, the islanding. Okay, when you have such a situation with inverters in islanding mode, so they are disconnected from the grid, they can't work in grid following situation. Again, because they need a reference and they don't have it. So all that together, that's also a kind of a black start situation. All together means we need uh, to take care of these extreme kind of like sensibility of the grid following and extreme reliance of that grid following to a existence of a strong grid. Okay, now before I move on, I want to like show this video. This video also explain the grid forming, introduction of the grid forming in a very good way. So it is gonna be a good.
A well-operated electrical grid is a balanced system. Generation and demand constantly vary, and we have to keep the system balanced all over Europe and ensure it operates at the correct.
Okay, let me.
Got safety protocols? Grainger has the Safety Pros 2 call. Shop our vast inventory of safety products at Grainger.com. Call.
A well-operated electrical grid is a balanced system. Generation and demand constantly vary, and we have to keep the system balanced all over Europe and ensure it operates at the correct frequency at all times. But the higher the renewable energy sources share is, the more fragile this balance is. So their introduction on the grid is a real challenge that Amprion and all other transmission system operators will have to handle. Presently, conventional generation plants play a key role in the electrical system. They use large rotating masses in their generators, so-called rotors, which keep the frequency constant due to their enormous flywheel.
Come on.
A well-operated electrical grid is a balanced system. Generation and demand constantly vary, and we have to keep the system balanced all over Europe and ensure it operates at the correct frequency at all times. But the higher the renewable energy sources share is, the more fragile this balance is. So their introduction on the grid is a real challenge that Amprion...
Let me play that, apparently. So I put that video on...
plants play a key role in the electrical system. They use large rotating masses in their generators, so-called rotors, which keep the frequency constant due to their enormous flywheel mass. A well-operated electrical grid stability. Take a bicycle as an example. When a cyclist at full speed stops pedaling, generation and keeps moving forward thanks to its momentum.
You can watch it.
And when he loses a load, his acceleration is contained by the bicycle's weight. It's the principle of inertia.
In my PowerPoint, so
with rotating machines, it's the same principle.
Go through that.
When the generation or the load varies, the rotor's inertia allows them to keep rotating, thus ensuring true grid stability. With renewable energy sources, it's way different. Their generating units do not have large rotating masses. They're connected to the grid by power electronics. Power electronics devices work rather like a musician who would read his score before joining the orchestra. So he only follows the conductor, namely the grid frequency. The devices observe the grid frequency in order to inject their power. Therefore, they don't offer any natural inertia, so-called spinning reserve, that would help ensuring system stability. So what can be done if the share of renewable energy is substantial? Two solutions are possible. The first one is to keep a minimum number of rotating machines, which among other functions can supply the necessary inertia in case of unbalance. In particular by using out-of-charge rotors that do not produce power, synchronous condensers. At Amprion, we already convert decommissioned power plants into synchronous condensers and design, erect, and operate new synchronous condensers. The second involves using renewable energy sources that can control the frequency by slowing down frequency deviation while emergency reserves come into play. This solution works if the renewable energy sources share is not too high, as is usually the case today. Because the analysis time that power electronics requires creates a frequency drop that, alone, the renewable energy sources cannot handle. Then what can we do on a grid with more renewable energy sources? Or even with 100% renewable energy sources? Here again, we have two solutions. The first one consists in keeping the conventional plant's rotors to make them work as synchronous condensers. They then draw their energy from the network and are responsible for the frequency and for guaranteeing its stability. The second
Another
solution
aspect
is to
that
use the power
grid forming
electronics
could help
capabilities
and
through
add is now.
renewable energy sources
On the
or
last
batteries
part,
to create frequency and to
again,
ensure its stability,
by those
even with
two
or without
capabilities,
rotating machines in
mandating the
operation.
frequency
In the
and
same way
voltage
as
level
present
and the
rotors,
output,
these equipments would become the
basically
conductors,
makes
and the other renewable energy sources would just have to follow the scores. This solution is called grid forming. Today, it's being developed and tested on reduced-sized hardware in the European Migrate project. Amprion will equip new power electronics units with this capability. And at Amprion, we think that it's a real solution for the future.
Rely on a grid. They also have the flexibility of working either tied to the grid or in islanding mode by themselves. So these one little change that
Old Spice Super Hydration Body Wash. The sweet scent of a honeymoon Fiji. Moisturized with vitamin B3.
Frequency and the voltage level.
You better not be using all the Old Spice.
Instead of bringing it to grid, okay, we could provide all these benefits and shape the grid forming inverters. Any question? Are we good so far? Okay. Let me see any question if it's in the chat room. No. Okay, now let's summarize the differences between the grid forming and grid following. Eventually, you could summarize it in the 4 categories. The difference between the grid forming and grid following. In the controller, the first category, which is the most important one. Okay. In grid forming, we establish voltage and frequency, as we said. In grid following, we synchronize those values to the grid. The role in the system for grid forming is they work independently. That makes them capable of black start and islanding situation. Okay, but the grid following requires a strong grid. Be careful about the terminology, not just a grid, a strong grid. Okay, inertia contribution. In grid forming, we provide virtual inertia. Why? Because the inverter would resist against the change in the terminal for voltage and frequency. That's basically the definition of the inertia. Okay, so it's kind of like virtual inertia. Okay, but grid following, there is no inertia, none, zero. Okay, so we don't have any resistance against the change. If there is any change, we follow it. The stability, which is basically, you could imagine that is a result of those 3 categories before. Grid forming improves grid stability. Why? Because it introduces inertia, operates independently, and establishes a certain amount of voltage and frequency. So our system state would become stronger. We have another force to keep the system state at the desired point. In grid following, the inverter would not contribute on stability at all. So if the grid is not strong enough or stable enough, inverter not only would not contribute to solve the problem, but also would add to that instability because it follows the grid. So it's like a negative loop, you know? So these are the kind of like the differences, like if you wanted to like generally compare the grid forming and grid following inverters. And there isn't a scheme like is kind of like to visualize what it means to have a grid forming and grid following inverters. Okay, that's kind of like maybe help you to have a better intuition. Any questions so far? Yeah. Now, when we talked about the grid following inverters, we said the whole aspect of the grid following would basically get squeezed into how we control it. Because the power circuit is the edge bridge or multi-level inverter or whatever topology that you wanted to like use, it doesn't change. What defines the grid following and grid forming is basically how we deal with the control system, how we control those switches, how we control the injection of the power at the terminals. Okay, so same goes here for grid forming. All come back to the control system. Now, since one of the biggest differentiation between the grid following and grid forming, let me ask you that. Based on the definition that so far we discussed and compare the grid forming and grid following, in the control system, what's your suggestion of one of the biggest difference between control in a grid following and grid forming? Any suggestion? We already talked about the grid following control system. Okay, you know how grid following works, and now you introduced how the grid forming works. Okay, generally. Now, based on the difference of their performance, their kind of like applications, okay, what comes to your mind in the control system of the grid following that we have to basically change it in the grid forming? Explain a little bit.
Because like the grid forming system needs to match the grid, so the control systems for it need to kind of imitate what the grid does for the grid following system.
It basically, that's correct. Now, what would change in the control system? If like you remember the control system that we had for the grid following. We had the PID control, and then we had the PLL, and all those stuff together would control our situation in grid following. Now, in grid forming, as you said, we are basically mandating the state of the system at the terminal, so we're mandating the frequency and the voltage. Now, what difference we should make in the control system based on that one little change? We don't need PLL anymore. Exactly. Because now we don't follow the frequency of the grid. We don't follow the terminal's frequency. So synchronization doesn't mean anything. We mandate the frequency at the desired level, which like in power system is 60 Hertz in the United States. Okay, so PLL does not have that influence in the grid forming that had in grid following. This is one thing. Another thing, in grid following, the control that we had was to read the voltage amplitude and voltage phase. Okay, and based on that, we ran a PID control and follow how much active power and reactive power we have to exchange with the grid. That was the idea. In control system in the grid forming, we still have to follow, okay? We still have to follow the grid demands for active power and reactive power. Okay? Now, for active power, we said that we could define the active power injection by defining the initial phase angle between the inverters and the grid. Okay? Doesn't change anything, it's okay. So we could do that again in the grid forming inverter because we don't have any restriction on the phase angle of the our voltage signal. Okay? But how about reactive power? We said reactive power is the amplitude of the voltage. Now, if we grid forming, we dictate the voltage, the amplitude of the voltage at the terminal. That means we basically lose one of our leverages in control system. Now we don't follow the voltage, the reactive power demand based on the level of the voltage. How we could deal with that? How we could, you know what I'm saying? So basically, we let go of the inverter and grid following to answer the voltage, the amplitude of the voltage that grids wants for reactive power consumption or generation. But now we indicating the amplitude of the voltage. How we could do that? Then it comes another aspect of control system, another methodology of the control system. Okay, which is basically a droop control. Okay, droop control tries to follow. It's like a we are going to talk about the droop control system in a detail in the next session. Okay, how it works. But the general idea of the droop control is similar concept-wise, is similar to the PID because it wants to mimic the output terminal demands. Okay, but what it does is basically it tries to like have a balance load sharing. So if there is a active power load demand, okay, an increase in a load at a terminal, that increase in a load at the terminal would disturb the balance of the generation and load. Okay, that disturbance would show itself into deviation in a frequency. What inverter sees, that increase of the load would make what inverter sees. We are going to talk about that, how it's happening, okay, later on in detail. But I wanted to like just give you an idea. The load increase, but what inverter sees is that, okay, the frequency of the grid is decreasing. It's overloaded. Okay, so I have to push for frequency. Does that make sense? So it would mandate more force to stabilize the frequency. How we can do that? By pushing active power into that terminal. And we balance the load and generation again. Reactive power the same. What it sees, it wanted to like keep the terminal at the mandated voltage. But if there is a huge load of like reactive load at the grid, what inverter sees is that, okay, the voltage of the grid is weak and is falling down. I have to keep it up. So it starts to mandating a stronger force over the amplitude of the voltage, compensating the drop of the voltage or increase of the voltage in case of like higher reactive generation in the grid, okay, and tries to like eliminate that effect. So it basically sees the load change either in active and reactive power as a disturbance, and it wanted to like keep the voltage and frequency at the desired level. So it see them as a disturbance and tries to eliminate them, that unbalance. This is the basic of the droop control. Concept-wise is similar to the PID. You can see that a PID wanted to like mitigate the error between set points and current point. Okay. Now the difference is that in droop control, the set points is solid. Okay, we don't change set point based on the measure. Set point is solid. Now, if there is a change at terminal, we have to push the grid to come back. Does that make sense? Is that clear for everyone? We can't say that the grid follows the inverter because basically they are no one follows itself. But the difference is that now inverter indicate the situation instead of following the grid. Locally, you could say that. Generally, no. Do you see my idea? Like, because grid is a huge kind of like network of system with a huge inertia. It's like you saying like that. Do you see the videos of the cat that terrifies a bear? You might see that in reels. Okay, so definitely, cat is not a scalable opponent to a bear, you know. But at a time, it could intimidate. You know what I'm saying? So the inverters, scale-wise, cannot change anything to grid in general, in larger scale. Locally, it could. At its terminal, it could mandate, the grid forming would mandate the situation. Now, if you have like millions of those grid forming inverters spread all over the grid, now the grid forming are dictating how the grid should behave instead of the conventional rotating machine. Make sense? So it's kind of like a accumulated, kind of like a what was the, I forgot the word, but it's kind of like the does it consensus? Am I pronouncing?
Consensus?
Yeah. So this is kind of like this kind of like effect. So everyone contributing, and overall it makes a huge virtual inertia that grid has to follow. Did I answer your question? Okay, good. Now, there are three main aspects to the control system. Most of the control system works with loop control. Even the other two categories are at the end basically works on a loop control kind of like methodology. But the difference is how you see the model of your inverters. Okay, in pure loop control, you see the inverters as a switching device, and you deal with them like if you want to like define the Laplace transform, you deal with them as exactly what they are. Okay, so the transfer function of the system is the same transfer function of the system as we had in PID. Those surges and R and L, the filter that we have, or C, you know. So in VSM, virtual synchronous machine, what we do is we replace the model of an inverter and try to define the dynamic of a grid forming inverter similar to formula of the rotary machine. Okay, in rotary machine, we have a differential equation that defines the mechanical kind of like behavior of that rotary machine regarding how to control power and, you know, phase and speed. There is going to be a damping factor, there is going to be an inertia factor, and a spring factor. If you remember about the mechanical physics that you passed before, okay? So we try to represent the inverters with those values. If you remember, like, for example, like in most cases, so far in other courses, you try to do that vice versa. So if you have a mechanical system or any kind of like chemical system, and you wanted to like analyze it in a electrical engineering, you would develop an equivalent model from that mechanical system using the electrical component. Okay, so you could have a better kind of like tools and like better kind of like understanding of what's happening and analyze that system. Here, we're doing the reverse kind of like method. We representing or modeling the inverter, that switching electrical device, with the model, with the equivalent model of a virtual kind of like a rotary machine. And we use all the concepts that are already mature, all the analysis are done on the rotary machine, and we apply it into that equivalent model that we have for our inverter. We are going to see a little bit more detail into that, but we are not going to focus on that. The focus of this course is on pure droop control. Okay, you can search on the VSM and the power synchronization control. They both work basically the same. Okay, but eventually what it does is they have to like apply the droop control in their output. So we are going to focus on the droop control itself. The modeling, how we model that, I'm going to keep it open. You can use any kind of like method that you want. In the assignment, you don't need to, but overall, keep it in mind. Okay. Now, droop control system. The mathematical formula for droop control, if you wanted to like get introduced to how the droop control works, is that, as we said, the grid forming wanted to indicate or like mandate a certain frequency and voltage in the terminal. We are going to use that to address the need for active power and reactive power injection. Okay, now what we do is that we define similar to like PID control. Okay, similar to PID control, we read the voltage at the terminal. Okay, we compare them to the mandated set point that we want to have, and based on that, we adjust the active power and reactive power injection into the system. The advantage of this droop control is that they are very simple to implement. They are very effective on power sharing and power control. Okay, and basically they are a proven reliable control system for grid forming. Next session, I'm going to go to the detail of the droop control, so don't worry about the formulas and how it works. I'm going to dig deeper in the next session. Okay, but the droop control lacks the concept of the inertia. Grid forming would imitate the inertia at the end of this droop control. Okay, but you don't see any concept, any parameter in your control system that represent or quantifies that virtual inertia. Meaning you don't have any observation of the virtual inertia or any leverage over that. Make sense? It is there. Droop control just can't see that, can't quantify that. Okay. Another limitation is the trade-off between accuracy and voltage regulation. Because, as you know, it's like a feedback loop. There is going to be an error. So, and it's a simple kind of like proportional type, like TI feedback loop. Okay, so there is going to be an accuracy kind of like problem when we deal with the PI control. We talk about that when we talk about the PID controller in the grid following. Same limitation would happen in the droop control. In virtual synchronous machine, the main difference is that because we're modeling our inverter as a virtual synchronous machine, now again we need PLR. Why? Because we wanted to like create a virtual rotary machine, okay, that works with a certain frequency of the grid. Now, the control system tries to catch up that virtual machine, regulate that virtual machine in order to mandate its own set point. Makes sense what I said? What I stated? That PLL is not synchronization. It's detection of the frequency. So we could define our model for virtual machine. Make sense? Is that clear? So, and as you can see in the system, we basically try to represent all those electrical components, change them to a mechanical component. The mechanical formula of a rotary machine basically is a differential equation that defines the change in speed based on mechanical power and electrical power. So in a rotary machine, if you inject electrical power, like 1 kilowatt of electrical power, but your load is 1.2, you are overloading your system, correct? So the rotary machine, the speed, okay, the speed of the rotary machine is gonna be decreased. Can you imagine, like visualize that? It's overloaded, so it start to lose the speed in order to provide the torque that it needs. And if it's underloaded, it start to speed up. Same here. The change in the speed of the rotary machine is defined based on the input and output power, electrical and mechanical power, and the characteristics of the machine, which basically is the damping factor, the frictions, okay, and the inertia that controls how fast and how strong the rotary machine would respond, the speed of the rotary machine would respond to the variation in the load. Is that clear? You don't need to like understand the formula. It's the formula that is in the mechanical engineering. Okay, but it's good to like have a visualization of what all of those components means. Now, we want to use that formula in order to mimic the dynamic of our inverter. So we want to deal with the inverters like a synchronous machine. And that J, that equivalent value for J that we define based on our calculation is that virtual inertia that we talk about. Now, in this mechanism of the control, we have the quantity of that virtual inertia that we create using grid forming unit. Are we good on that? Now, you could go over that. I don't want to like go deep into the VSM, but it's a very good kind of like method if you wanted to like have a better kind of like visualization of what we're talking about in a grid forming inverter, because you have the intuition of how the rotary machine works. Now it would let you to like kind of like make connection between the grid forming inverters parameters and the rotary machine parameters, and you can have a better kind of like intuition about what we mean by controlling the grid forming inverters. Now, since we do not follow the grid anymore, that means we do not rely on the stability of the grid anymore. That means if we wanted to like have a system, independent system, we have to make sure after every setting, we have to make sure that our system is fully stable and fully functional. So one of the big differences between designing a grid following a grid forming is that in grid following, you didn't have to worry about the stability. Actually, it wasn't stable. If the grid was unstable, the grid following is screwed. Okay, but in grid forming, we are saying that we are independent. So stability-wise, we have to check what are the unstable situation is. So we have to avoid that. So how we could do that? One is impedance-based system analysis. Okay, we deal with we model our inverter as a dynamic impedance. That dynamic impedance would have a transfer function like all the other impedances, like the transfer function of the inductance is Ls, correct? Or for capacitance is 1 over Cs. This is the transfer function of those impedances. Or for resistance is resistance itself, S. Okay, it's the Laplace transform of those impedances. Now in inverter we have a dynamic one, so it's a more complicated formula. Okay, and it's dynamic. Okay, it's changing. Now we have to, when we have a more complicated formula, like if you have a GS, the dynamic, the impedance representation of your inverter as F of S over H of S. Okay, when we talk about the stability, what we talk about, what are the unstable situation? Are you familiar with the Laplace transform? What would be the unstable situation for this transfer function? What are the point that we have to avoid? In calculus, if you have you should not have a denominator equal to 0. So any value that makes HS equal to 0 is forbidden. Are we good? Now, any value that make Fs equal to 0, what's that situation? It basically means those points makes our system obsolete. So it's 0. On those points, we don't have any system, basically. You know what I'm saying? So we have to avoid a certain point, and we have to see, okay, in different kind of like situation, in different states, okay, where we are in respect to that zeros of the denominator and zeros of the numerator in the graph of those states, and we have to avoid those unstable states. I hope you know that like Nyquist stability criteria. This is what it means, the Nyquist stability criteria. There's a Nyquist graph. You put the poles and zeros, and you find out where are you, what is the possibility of become unstable or on the stable side. Okay, so try to like read about the Laplace transform and Nyquist stability. It is very handy. Try to learn that. It is very handy and it's very important concept. As an engineer, you should know that. If you don't, learn them. It is important. Let's move on from that. Don't want to like complicate this concept because I'm gonna talk about these concepts, the virtual impedance and frequency time domain analysis after the midterm because it's more system analysis. And Yeah, they are more system analysis. So I don't want to like give you the information that you don't have the fundamental concept in your mind. So I want to like have some of the ideas beforehand. Any question so far about what we discussed in introduction of the grid forming inverters? Any confusion or like any concern about what we discussed today? No? Guys in the Zoom? Okay. So if that's it, this is it for today's session. Next session, I'm gonna talk about the Droop control itself because it's the heart of the grid following, and we have to like know how the Droop works. Okay. And after that, after the Droop work, basically we are finished with the concept that we wanted to like talk before the midterm. Okay. I am gonna give you the next week. So next week, which is the week before the break. Okay. We would not have any lecture. I wanted to give you that week in order to like work on your midterm report, and I extended the midterm report to the 16th. Okay. So you can work on your midterm report on the next week, not this week. This Thursday, we are going to talk about the group control. So we have class. Next week, we don't have a class. Put the time, use that time on your midterm report or finishing your assignment or resubmitting your assignment. Okay. And after the break, we are going to move on to the system perspective of the inverters and talk about those power concepts and like these stability analysis and how we deal with the inverters in a power grid. Are we good? Any question? No? No, unfortunately, because of the problem that we had for delivering the parts, and they still didn't deliver some of the components. I waived the hardware part of the assignment for assignment 1 and assignment 2. If you are interested, if I get those parts eventually, hopefully, I don't know how to like pray for that. But if I get those parts, I will distribute it. So if you are interested personally to doing that after the break, after the midterm, we could work on it. If not, it's not a mandated kind of like task for our course. Are we good? Any other question? No? Okay. Thank you very much and have a good rest of the day.